OK, second model I want to talk about today, which is also kind of beloved by complexity theorists and quite natural and kind of enjoyable, is the model of Boolean circuits. And these are also a really nice model for computation because, again, like Turing machines, they're like 100% like concrete and unambiguous. There's no like wishy-washiness about like, oh, what is the complexity of this circuit? I mean, you know what a circuit is, right? It's like, looks like this. It's got some AND gates, probably some OR gates, some OR gates here. I don't know. Whatever, some NOT gates. You have the inputs, x1, x2, x3. So this is a thing that computes functions. That's probably valid. It computes functions that map binary strings to binary strings. I should say Boolean functions. OK, we'll talk a lot about Boolean functions a few lectures from now. And the circuits can have multiple outputs. So you can have like circuits that output long strings. But often you only worry about outputting a single bit, a yes/no answer. And as I said, these are like a nice model of computation, and they have like simple properties. And you can do things like exactly count the number of gates in a given circuit and so forth. So let me say a few definitional things about circuits. Just to make sure we're on the same page. So these are DAGs, directed acyclic graphs. And the nodes are called gates. And when you're defining circuits, you have to make a decision about like what your allowed set of gates are. And there's like, I don't know, 2 or 3 like reasonable choices, and neither is more correct than the other. So you just have to accept the fact that like every time you start talking about circuits, if you want to be really careful, you have to specify like what gate set you're allowed. So maybe one might write B for what's called the basis, which is the set of allowed gates. Okay, let me continue, I don't know, over here. OK, and actually, besides these gates that are like AND and OR and NOT and so forth, you have these special gates at the bottom labeled x1 through xn, which are called the input gates. And usually there's something that's like marked as the output gate, of course. And this object, when you plug in bits for x1 through x4 or xn, it computes a Boolean function in a natural way. And unlike with algorithms like Turing machines, you don't normally talk about like the time for a circuit or anything. The 2 main measures of complexity for circuits are size, which is the number of, usually defined to be the number of non-input gates. And it's somehow, well, let me just say one more thing. The other popular measure of complexity is depth, which is the longest input to output path length. OK, and circuits are actually a kind of reasonable model for parallel computation. So like a good analogies between circuits and algorithms are to think that like the depth is kind of like the parallel time for the algorithm, and the size is kind of like the parallel work or the total amount of work. If you're not into parallelism, then like the best comparison between just Turing machines and circuits is like size is kind of like time. Because you can evaluate a circuit in time roughly proportional to the number of gates. And roughly speaking, you can convert a Turing machine running in time t to a circuit of size t log t that does the same thing. I guess just as one more small comment, usually you're allowed like constantly 0 and constantly 1 gates that are like free. They don't cost you in size. So like, you can just have like a 1 here. OK, so let me say just a few things about popular choices for the set of allowed gates, the basis. And I'll only mention 3 different choices here. One popular choice is, just you get NOT gates, and you get binary and an OR gates. Okay, binary means it has fan-in too. That's pretty common. These are usually called, or sometimes called, De Morgan circuits. Another possibility is you can allow, for example, all 2-bit gates. Okay, so you can allow, like, I don't know, XOR of 2-bit gates. And one more thing I'll mention, it's similar to the first one, but it has NOT gates and like any fan-in and an OR gates. Okay, so I guess somehow I implicitly started using it here where this OR gate has 3 wires fanning into it. Okay, and one nice thing about these 2 cases is that they're simple. Every gate takes either 1 or 2 bits. One nice thing about this case where you're allowed arbitrary fan-in is that now you can actually do some interesting computations with constant depth circuits, which is like constant parallel time algorithms. Right? If you only have constant depth and your gates only look at 2 bits, then you can't even have the circuit that like looks at all the input bits unless its depth is log n. But here you can actually do some interesting things, like for example, add 2 n-bit numbers in constant depth. Okay, so I'll give some quick examples here. So if you wanted to compute the extremely simple function, the AND function, that on n bits, well, you can do it in size 1 in, let's call these models 1, 2, 3. In model 3, you just need one, you explicitly have a gate for that. Okay, but in model 1, where you just have fan-in 1 and 2, what is the size and depth of like a good circuit for computing the AND? Yeah, you can make a little tree of binary AND gates and do it in size order n and depth order log n. Okay, as I said, one sort of similar to Turing machines, and actually even more so than Turing machines. One nice feature of circuits is that you can be like brutally explicit about their complexity, like size and so forth. So I'm just going to read you a fact without writing it on the board. There's this theorem of Meyer and Stockmeyer, 2 complexity theorists. They proved it in 1974, and it was about a certain problem called WS1S. Which is the problem of deciding if a sentence, an input sentence in a certain form of second order logic over the integers is true or not. I don't even know exactly what the definition is, but it's some problem about logic, whether a sentence in some form is true or not. It's a decidable problem. It's not like it's an undecidable problem or anything. It has an algorithm. But they show that any circuit, actually in model 2, that solved this problem on sentences of input length 3,660 needs to have size at least 10 to the power of 125. So, you can actually prove explicit complexity results that are kind of dramatic like that. Let's do one more little example, just because somehow I got real excited about these 2 problems of palindromes and sorting. Let's talk about palindromes on circuit model. So let's say we want to solve palindromes with the circuit. What would we do? Well, this is quite easy as well. Let me assume, just to be simple, that like n is even. So even this is sort of going to be like implementing the actual algorithm where you compare the first and the last bit and the second and the n-1th bit and so forth. So one way to do it, let's say, is let me first on the side say that like if you want, you can build like an equality gate. Let's say we're working in model 1. If you want, you can build a little equality gate for 2 bits. It's a little confusing. By doing, let's do the OR of either 2 bits are equal if either they're both true or if they're both false. OK, so there's some little gadget given 2 bits using and or not gates that checks if these 2 bits are equal or not. Or if you're in model 2, you can just be like, oh, I have an equality gate. And then using this gadget, we can check if a string like x1 through xn is a palindrome by doing the following. Well, I just wrote the bits in a funny order here because I'm going to check if these are equal in pairs. And then actually, let's say I'm working in the third model because I want to do the following. I want to AND these all together. OK, so here I use the power of unbounded fan-in. And this solves palindromes with a number of gates that's going to be like, I don't know, 5n-ish. But anyway, this will have size order n. And this will have depth. Maybe, I should mention one thing, another thing. Usually negation gates are also considered free in this model. Because actually, if you have and, or, and not gates, you can actually push all the not gates down to the bottom by using like De Morgan's laws. And then once they're at the bottom, you kind of can just pretend that the inputs are like x1 through xn together with the negations of x1 through xn. Then you only have to worry about counting and or gates, and it's kind of convenient. So in this case, if you do that, this will look like a layer of and or and, so it'll have depth 3. So this is another example of how you can solve a non-trivial problem in constant depth in this model where you have unbounded fan-in and or gates. Yep.
I just want to say choosing 2n instead of x and x.
Thank you. Yeah. Does anybody know how to do it in depth 2? Well, think about it. Any solution? Here's a trick. Here he did this equality gate by doing an OR of ANDs. But you could also have done it with an AND of ORs, right? Built a tiny little CNF instead of building a tiny little DNF. And then if you'd use that here, these all would be like ANDs of ORs. But then you have ANDs feeding into an AND gate, so you can just merge them all into one giant AND gate. So you'd have like one giant AND gate and some ORs at the bottom. So that's a little trick with circuits. If you have like layers of the same type, like all ANDs or all ORs, you can merge them together. OK, so now one thing about circuits, which is like a little bit annoying, but we should talk about it. These are kind of contradictory. I'll just put this here. That we should talk about it is the way circuits are, they're only designed to take inputs of a certain fixed length, right? I mean, this circuit has like 2n inputs. Whereas for like Turing machines or like a normal algorithm, you assume that your input is just any old length. So if you actually want to solve a problem where the input can be any old length, you need not quite just a circuit, but you need something called a circuit family. And a circuit family is nothing more than like a bunch of circuits, one for each input length, where Cn has n inputs. And such a circuit family decides a language L, or a problem L, if the nth circuit decides the language on length n strings. OK, so it's kind of annoying if you want to talk about the multiplication problem. You need one circuit for multiplying. Oh, you want to talk about solving the palindromes problem. Really, you should have one circuit for solving palindromes on length 1, a different circuit for solving on length 2, on length 3, on length 4, and so forth. OK. So just because it's going to come up later, I want to tell you the names of some different classes, complexity classes, classes of problems that are defined by how well circuits can solve them. And this being complexity theory, these complexity classes have like terrible names, analogous to the terrible names like NP and L and all those other horrible class names. I refuse to even tell you what the letters stand for. It's so bad. So the first complexity class I want to mention is called AC0. And this is all the languages or algorithmic decision problems decidable by a circuit family of the main thing is constant depth, order 1, and size poly n. Okay, here I'm talking about being in like model 3 where you have AND and OR gates of any fan-in. So these are all the problems that you can solve sort of efficiently in terms of work, polynomial amount of overall gates or whatever, but in like constant parallel time. Okay, so these are like very efficiently solvable problems. They include things like palindromes, and although it's not quite a language, it includes things like adding two n-bit numbers can be done in this class. A bigger class is called NC, and this corresponds to the same story, but polylog n depth, and still poly n size. Okay, and this kind of corresponds to problems that can be solved pretty efficiently in parallel. So still like polynomial total amount of work, but like wall time, parallel time that's like poly log n. Yep.
And this is when you don't have arbitrary fan-in, right?
Okay, once you get to here, it doesn't matter whether or not you allow arbitrary fan-in. It's an excellent question. I thought about this very question when making my notes. It doesn't matter anymore because let's say you have a solution like this, poly log n depth, poly n size, using arbitrary fan-in AND gates. And then you're like, I'd rather actually work with only binary gates just to be simplified. Yeah, exactly. You can take a big AND gate with fan-in, whatever, poly n, and you can convert it to a tree of binary gates. And this will add at most like a log n factor to your depth, and at most a poly size to your circuit size. Yep. Yes, it stands for Nick's class. That's right. Good old Nick Pippinger. And the last one I'll mention is called p/poly, and this just means poly n size. Okay. So things that can be solved, quote unquote, efficiently with circuits. And just to compare this with Turing machines, this is a fact that was proven by Pippinger and Fisher. I guess that's Pippinger, Nick of Nick's class. So maybe he deserves to get his name on the complexity class. Multi-tape Turing machine that solves a problem in time. I think I mentioned this actually. T of n is like simulable by circuits of size roughly T of n. It's order T of n log T of n. Okay, and this is why there's sort of like an analogy between circuit size and algorithmic time. You might ask about the reverse, like, okay, conversely, let's say I have a circuit of polynomial size. Does that mean, let's say I have a circuit family of polynomial size that decides a language. Does that mean that there's a polynomial time algorithm for deciding that language? And the answer is no, but due to an annoying reason, which I'll now discuss. So it's the reason known as uniformity, and it refers to this like weirdness that like circuit families have like a different circuit for every input length. And potentially that can allow you some weird stupidities. I bring this up because it's like an important point in complexity theory, and it'll come up mildly when we discuss quantum computing. So here's a fact to illustrate the annoying weirdness. I'll call it an exercise for you. The halting problem is decidable by circuits. It's decidable by circuit families of size, I don't know, O tilde of 2 to the n. And that's unsatisfactory when you remember that Turing proved that the halting problem is undecidable. It's kind of disturbing to think that there's a family of circuits that decides it. But the reason is just, every Boolean function at all, mapping n bits to 1 bit, has a circuit, can be computed by some circuit. You can write down the whole truth table for the function and make even a DNF that computes that truth table. So in fact, Claude Shannon in 1949 showed that every function on n bits has a circuit of size, in fact, order 2 to the n over n, so around 2 to the n. And therefore, in principle, there exists, the halting problem when restricted to inputs of length 100 is just some function mapping 100 bits to 1 bit. So there exists a circuit with 100 inputs that decides the halting problem on 100-bit inputs, and of size 2 to the 100 or so. And there exists one that solves it on 101 length inputs, and so forth and so on. So there exists a family of circuits that solves the halting problem. But this is kind of dumb, right? Because now you see just saying that a circuit family decides a language if these appropriate circuits exist, it's kind of stupid because you're OK, please tell me these circuits so I can use them to solve the problem. And the definition's response is oh, I only promise you they exist. I'm not telling you how to get them. So you can define that stupidity away. And let me mention that definition. One says that a circuit family Cn is uniform if just there exists an efficient algorithm, like a Turing machine algorithm, or I don't know, a Python algorithm or whatever, that runs in time poly n for outputting the nth circuit. Okay, what it means is you should have some algorithm that you tell it 100, and in poly of 100 time, it prints out the circuit of length 100. Okay, which means you have an efficient way to get the circuit. And so if you always insist that your circuits have this uniformity property, then there's a real equivalence between circuit size and algorithmic time. For example, the poly-sized circuits that are also uniform decide the same languages that are decidable in polynomial time. It decides it's p. Yes?
Is that uniformity baked into these definitions? Is mixed class implicitly
Oh yeah, it actually depends on who you ask. Whether when you write AC0, does that mean uniform AC0 or just non-uniform AC0? I think a majority of complexity theorists would vote that it means non-uniform, but since it's it's contentious, you should just say when you're writing your paper which one you mean, if it makes a difference. Okay. As I said, one reason I bring it up is actually when we talk about quantum computing in the one lecture on that, it's extremely convenient to define quantum computing in terms of circuits and not in terms of quantum Turing machines. But then you want to make sure you don't suddenly have oh, quantum circuits can solve the halting problem for this dumb reason. So now I can say, oh, they have to be uniform as well. Okay. Again, as mentioned, one nice thing about circuits, and I mentioned this with that lower bound about the WS1S logic problem that requires size 10 to the 125 on inputs of length 3,660, is that it is possible to sometimes show lower bounds for circuit size. And trying to prove lower bounds on circuit size, the number of gates you need to solve some problem on a circuit, was very popular in the 1980s, and then it kind of fizzled out because it turned out to be pretty hard after all. Yep?
Kind of similar to the last question, I was wondering if uniformity actually makes a difference if you only restrict yourself to poly-n circuits. Can you get these kinds of examples?
The question was whether you can get some annoying examples like this if you restrict yourself to poly-n size circuits. Yeah, you still really want to have it. For example, the halting problem in unary, if you remember all your complexity theory definitions, I'll just bring it up, is also undecidable by Turing machines, but it has order n size non-uniform circuits. So you can still engineer these idiocies even with the poly-size restriction. It's a good question. OK. So let me just mention to you some facts that are known. One was proved by Shannon. Not only did he show that in 1949, every function, n-bit function has a circuit of size order 2 to the n over n, he showed that there exist functions on n bits that need this size. Let me just say needing circuit size omega 2 to the n over n. OK, so it's a non-constructive argument. It's a counting argument. And it just shows there exist functions, Boolean functions, that require exponential size circuits. So, back in the 80s, they're like, maybe we can find an explicit function, quote unquote explicit function, that requires exponential size circuits. Like maybe we can show that solving SAT on length n inputs requires exponential size circuits. And in general, like explicit usually means like in NP, for example. And turns out that's really hard. People worked super, super hard to prove circuit lower bounds. And here's the best that they could do for general explicit functions. This was proved by Iwama and Morizumi in 2002, building on a result of Lashish and Raz from 01. There exists a language L, so like an explicit problem. In fact, it's even in P, so it's not like SAT or anything. Needing circuits of size 5n minus little of n. And this is when the basis is not and binary and or. And like that's the world record for an explicit problem, best circuit lower bound, 5 times n minus little of n. So that goes to show that, in complexity theory, proving lower bounds is pretty hard. Actually, there's a very exciting result from 2016 by Fine, Golovnev, Hirsch, and Kulikov. They considered the exact same problem, but in the gate set where you can have like any binary gate. So this is even a more powerful circuit model because there's more kinds of gates. So it's even harder to prove circuit lower bounds. And they got at least 3 and 1/86th n minus little of n. Okay, so I put those up as like a little joke to illustrate that proving circuit lower bounds is very hard. And one last thing I want to mention is you can consider the problem of sorting with circuits. Actually, imagine sorting just single-bit numbers. Really, that's just counting the number of ones in the inputs and then outputting the count in unary. And some special cases of that are outputting the least significant bit, which is like, are there an even or odd number of ones in the input? And that's called the parity function. And also outputting the most significant bit, telling if there's more or less than half of the bits are 1. That's called the majority function. And these were proven to not be in AC0 by first Sachs and Sipser in 81, and then succession of improvements culminating with Hostad in 88. And another example is multiplying two n-bit numbers. OK, so these are actually showing that these cannot be done by polynomial-sized circuits if the circuits have to have constant depth. So it's some kind of lower bound, but the constant depth is an extreme restriction. You can compare this with adding two n-bit numbers, which actually can be done with a constant depth circuit.